Hello, welcome back to Piers Rocks. Today, Rust programming on the STM32. I've just soldered up a batch of my software-defined retro ROMs that replace the ROMs in these old computers, and I realised that I wanted some kind of test program for them to make sure that they've been soldered up properly. I can test the actual core functionality, the address pins and the data lines, just by writing a kernel ROM onto these and sticking them into a Commodore 64, turn it on. If it boots and doesn't crash, then all of that functionality is working fine. However, on these boards, I've also got a bunch of jumper pins at the top here and an LED at the bottom that I want to be able to test. My go-to language for writing simple programs like this is Rust. Today, Rust has a great ecosystem and tooling around it. So there's a significant number of libraries for functionality that you're going to want to use in your application, and the tools are all there to make it really easy to build and flash the firmware to your device. And Rust has a really significant advantage that Python doesn't have, and that's that it's really strongly typed and it's a compiled language. So once your Rust compiles, and actually it's not that difficult to get it to compile, we'll look at that in this video, then it's actually going to work. You're not going to crash a few seconds or a few minutes into your program because you mistyped something. So the application that we're going to develop today will be from scratch in Rust, and it's going to do two key things. One, it's going to flash the status LED on a timer, and two, it's going to detect when the jumpers get closed and opened, and we're going to use interrupts for that. We're going to be developing this within the embedded asynchronous environment within Rust. This is going to make it really, really easy to have multiple tasks running simultaneously on this device for both flashing the LED and detecting each of the GPIOs. So while this application I'm developing for my own hardware, which is STM32 F4 based, everything in this video is going to be suitable for running on multiple different STM variants and PCBs. Now, to get started, we're going to use Cargo.toml to create a directory for us, and we'll call it STM32 GPIOs. So here's what Cargo.toml has created for us, a skeleton project. So we need to go in and make some modifications to this. First thing we're going to do is add what we need to Cargo.toml, which is the main configuration file for a Rust project. And we're going to add a binary to this, and we're going to call it, I guess, STM32 GPIOs, and the source file is at source main.rs. Now we also need to add a bunch of dependencies for our project, and I'm just going to copy and paste those in from another project and then I'll explain them. So we need a bunch of Embassy crates. So Embassy is the main asynchronous environment that we're going to be developing our application in, and we'll come on to a few of those features in a moment. We also need a couple of Cortex-M crates. These are to actually support the architecture of ARM processors that are used in the STM32 MCUs. And then we need a few others, essentially, which handle panics and logs for our application. So we need a panic probe so that when the probe.rs tool that we're going to use for flashing and connecting to our device can actually hook in when there's a panic in our program. And deformat are being used for logging purposes. Essentially, deformat are great for doing logging on embedded platforms because your RAM and flash typically limited on these platforms, and logging you generally want large amounts of strings because your logs are string outputs. Well, deformat doesn't include the strings in the binary that's being uploaded to your embedded processor. Instead, it just uses unique identifiers for each log strings. That's what's on the embedded device itself. The strings themselves are kept on the host within the debugger, and it can look up those strings based on the IDs it gets when a log is produced. And we're going to be using RTT for logging here, which is real-time trace. And that's essentially the embedded device will be writing all this logging information, the IDs and any variable values that the logs use, into a circular buffer at runtime. And then probe.rs, the debugging tool that I'm using, is going to be pulling those out, looking up the strings from the indexes and outputting those to me in human readable format. Let's come back to the embassy crates that we're using here. We're going to need 3 crates for this application, 3 embassy ones. We're going to need the executor crate that I will quite often call executor. Don't know why, just a hang up that I have. That is actually handling the main scheduling environment that we're going to be running within. We're going to be running multiple different tasks for application, and embassy executor is going to be handling that for us. We need the STM32 embassy crate. This is going to give us access to STM32 specific hardware peripherals. The key ones we need are the GPIOs and also external interrupts, which we have configured here. And then we also need the embassy time crate, and this is going to give us access to timers, so we can delay or wait for certain periods of time in our application. For example, to flash our GPIO, we're going to want to turn it on, wait for 500 milliseconds, turn it off, wait for 500 milliseconds, and repeat. And that's going to be done, that waiting is going to be done by embassy time. So that should be all that we need in our Cargo.toml. There's a few other things to set up though before we start writing code. And we're going to need a .cargo file so we can add some additional configuration to Cargo. And I think it needs to be config.toml. And inside here, we're going to put a couple of different things. We're going to tell Cargo what target that we're building for. So this is the target that's based around the ARM processor that's in my STM32s. These are STM32 F4s, so I need the thumb V7EM target. This is going to make sure that the code produced is actually the right machine code for this processor. The next thing that we need is an instruction to Cargo what to do when we do a Cargo run for this target. And rather than running the application locally on my PC, well, it's not going to work because it's the wrong architecture code, it's going to use the tool build.rs to actually flash the binary we've produced to one of my devices, and then it's going to attach to it and retrieve an output logging from it. And this is an instruction that tells build.rs how to do that. In particular, I'm telling it what my chip is. I'm using an F411RE chip. Then we need some development and release profile information. In particular, in the release case, we do need some debug information in the ELF file, the binary file that's being produced by the compiler. That's so that build.rs can find the right bits of the file to flash to the processor, and can also access the deformat string information itself and use that at runtime once it's attached to the target. And the final thing here is we need an environment variable, which you could just pass in on the command line, but this is configuration information to deformat about what log level to actually produce, and I want to get logs out that are at level info and above. That should be all we need from our cargo config.toml. Next thing we need is a VSCode configuration file, and I think this is called settings.json, and this is going to tell the VSCode, my IDE, to run the Rust analyzer on my code as I'm developing it. So I'm just going to pull that in from another project, and there's a few bits and pieces I don't think I need, so I'll remove them. So this is basically just telling VSCode to run the Rust analyzer on my code as we go. And we're going to restart the Rust analyzer at this point, given I've given it some additional configuration. Now, it'll be off trying to compile my project. It might fail at this point because we've not finished setting everything up. So one more thing to set up at this point, and that's to make sure that my Rust environment actually has support for the ARM target for the STM32 F4. So I will make sure that that's installed by running rust-up target install and then my thumb v7em none eabi. And it is already installed, so at this point I should be good to go. Famous last words, one more thing I need to add to my cargo.toml, and that's that I need to tell the embassy STM32 crate what STM32 variant I'm using so that it can include the right linker files for me. And I think that's the right format to use for embassy STM32. So it now knows I'm using the STM32 F411, and the R stands for 64-pin package and E stands for the size of flash I've got on this chip. Now, because we're developing an application for an embedded target, we're going to need to give the linker that's used by Rust some special instructions to create the right binary for this, to make sure that the various bits of machine code that are being produced end up in the right location, both within the image that's being flashed here and that it gets flashed to the right location. And the way we do that is with a build.rs file at the top level of our project. And this is a file that you generally use where you want to give the compiler extra instructions, or you want to do some work maybe to auto-generate some code before your project proper gets built. And here you need a main function. And what I'm going to be doing here is just adding a bunch of print statements, which are additional instructions to the build environment as things to include. So the key things I need are, first of all, I want to tell Cargo to actually rebuild the project if that deformat log environment variable changes. If I want to reduce the log level down to get all trace and above logging, then I actually need the compiler to recompile my binary because it will not have included those trace statements previously. And then we also need to tell the compiler how to actually link deformat stuff. Or remember I said that strings are not actually being included in the binary that goes on the device, they're used by the host. So the defmt.x linker file is going to ensure that happens. And then we need a couple of link statements for the STM32 binary that's being produced. This first nmagic one essentially just makes sure that the binary is nice and small and compact. But this -t link.x is crucially important. This is what pulls in the STM32 specific linker file and links our binary in the correct way. When I added that STM32 F411RE statement to feature to Embassy STM32, that's going to ensure that the correct link.x file gets produced by the build, and then this statement ensures that it's actually used to link my completed binary. At this point, we're ready to tackle our main function, and you can see we've got a couple of different compile errors. That's because we don't use standard main functions when doing Embassy embedded development. So we'll delete that, and we need to start off first with a little bit of boilerplate. We need to indicate that we're not going to be using the standard library. It's typically not available when doing embedded development. And also that we will not have a standard main function. We will have a main function, but not a standard one. So let's create that now, and we need a couple of users from Embassy executor to do that. We need the spawner object and we need the main macro. We can then create ourselves an Embassy main function, which needs to be an asynchronous function because everything you do within Embassy is asynchronous programming. And if you're a little bit uncertain of asynchronous program, I'll explain it to you as we go along. And our main function takes one argument, which is the spawner object that Embassy is going to give us, and this is going to allow us to spawn our own tasks. And that should be all we need. And we've got a few errors here. The Rust analyzer is just busy off compiling our code, so I'm hoping they're going to turn into warnings any moment. So I got rid of the warnings just by doing a restart of the Rust analyzer server, and they've gone. So we have just one warning at the moment from the compiler, but this executable won't compile right now. There's a few other bits of boilerplate we need to add. We need to include a panic handler so that probe.rs, if we hit a panic in our embedded application, can actually hook into that panic and we can debug the application. We don't need to use anything from panic probe, we just need to use it as underscore. We're also going to want to use deformat RTT, the real-time tracing I spoke about earlier. So again, we include that, and we use that as underscore. At this point, if we bring ourselves up a terminal, then I'm hoping that this is actually going to build successfully. Yeah, it's built successfully. So we have actually got a binary out of this. It's not going to do very much because the main function literally does nothing. And we get the warning about the unused variable. But we're good to continue at this point. We know that we've set up our project and our build environment properly. So at this stage we're ready to do something useful with our application. First thing we need to do is we need to initialize the STM32 hardware abstraction layer within Embassy, and we need to get the peripherals object, which we do like that. This will actually now allow us to retrieve hardware peripherals like the GPIOs, which we're going to be using in our application. Now what we're going to do is we're going to create a task to flash our GPIO that we have an LED connected to right at the bottom of my little board here. So I want to create an embassy task at this point. In fact, I'm going to use the macro here, and then I can just declare this next function as an embassy task. So I want another asynchronous function. I'm going to call it flash LED, and I'm going to pass in a mutable GPIO object. It needs to be mutable because I'm going to want to actually change it and turn it on and off. And the type I'm going to want for that is this output type, which is from the embassy STM32 crate from the GPIO module. So that's magically included that for me. And I also I need to have a lifetime specifier on this object. And I'm going to be passing in a static lifetime object. So an embassy task is going to live for the entirety of the lifetime of the program. When you start it, it never actually executes. And therefore, any objects that you pass into it must live sufficiently long. So you have to declare the lifetime on things like peripherals. And you don't really need to worry about this too much, because when you retrieve that GPIO from the peripherals structure, which we're going to do in a second, then this lifetime is handled for you. Then we need to declare the return type, and we use exclamation mark because this function is never going to return. It's going to sit in an infinite loop forever, flashing our LED. And that's pretty simple. We're just going to go GPIO set high. We're then going to wait for a period of time, and we're going to use embassy time timer for that. And we're going to say after milliseconds, after 500 milliseconds, we'll come back to a wait in a second. We'll set that low. And then we will wait another 500 milliseconds. That's literally all we need for flashing an LED. Now, what's this await call? So what this does is it tells embassy that we want to wait for this to complete. In fact, what it's doing under the covers is I would use the term yielding to the scheduler and saying to the scheduler, I'm done for a while. I would like to be rescheduled in 500 milliseconds, please. And the scheduler is going to go off and schedule other tasks. And if there's no other tasks to schedule, just sit there waiting until it needs to reschedule this task again. So the scheduler is guaranteeing with this call not to call us back before 500 milliseconds is up. It may be a little bit after 500 milliseconds if it's actually busy doing something when that 500 milliseconds is up. But this is essentially, I'm thinking of it as a yield back to the scheduler, so the scheduler can schedule other things to do work. And this is one of the bits of magic that makes asynchronous programming work. That's all we need for our task, and we'll see it's compiling just fine at this point, that new task that we added. So the next thing we need to do is we need to retrieve the GPIO from the peripherals object that we have called P, and we need to actually spawn this task. So let's get the GPIO, and we're going to call it LED GPIO, and we're almost certainly going to want that as mutable because we're going to need to pass it into the task as mutable, as changeable. And the GPIO that I have my LED connected to on this board, I think, is port B pin 15, which I think in the STM32 land you access like that. So yeah, we've successfully retrieved that particular pin. Now, this is one thing I'm not too sure how I feel about in Rust, and the type safety actually makes working with GPIOs a little bit of a pain. What I have here is an object which is of the type PB15. It's not of a generic pin type, it's of a specific pin. And you'll see my task takes an output type. It doesn't take a PB15, and that's so this task will work with any type of GPIO. You need to transform this PB15 specific object or PA3 specific object or whatever pin you're using into an object that can be passed around and used sensibly. And there are effectively 4 different types that you can use in Embassy. It varies a little bit based on the hardware platform you're using. Obviously STM32 here. There's input, output, any pin, and a flex pin. And any pin really just allows you to convert all of these different pins into a single type and use it in a very generic fashion. Input turns it into a pin that will be used for input purposes, obviously. Output for output purposes, obviously. And flex, you can switch it between input and output pretty easily. I want an output pin, so I'm actually going to turn this into an output pin right now in this assignment line. And I'm going to call output new, pass in the pin number, and there's 2 other arguments that I need. I need an initial output level. I'm going to say this should start its life output high, and that's because my LED turns on when I pull the output low, and level high. The other thing that you need is you need a speed setting. So if I was implementing bit banging some really performance critical protocol here, I might set the speed to high. I'm just going to set the speed to medium in this case. So now I have my pin as an output pin. I can pass it into my task. So let's spawn that task. And the way we do that is we call spawner, and then I'm going to call must spawn my flash LED task, passing in the GPIO. Now the compiler's barfed on that because actually I need to use dot instead of a double colon there. So the compiler's telling me that I don't need LED GPIO to be mutatable. That's because I'm not mutating it in this function, and when I pass it into flash LED, I'm passing ownership of it across to flash LED. At this point, Rust Analyzer thinks that the application has compiled. So I suggest we flash it to this device and see what happens. So at this point, I have my debug probe connected to my target, and I should just be able to run cargo run, and it should do any building that's required and flash the application to the chip, and we should see the LED, which is up here, start blinking. It's flashing it, and there we go. It started blinking. So that's our basic blinky program sorted. Now let's move on to detecting GPIO state based on interrupts. Before we actually add the interrupts, I just want to add a bit of logging to this as well, to show you how to do that. So the logging macros are all part of the deformat crate. I like to import all of them, even though I may not use them all. So we want debug, error, info, trace, and warn, because they've got to be in alphabetical order. And just in case we don't use them all, we will include and allow unused imports statement so the compiler doesn't complain. So we will add a log starting STM32 GPIOs. Okay, so we've got our LED flashing. So now we need to create some external interrupt objects. And we'll do it for just one of the jumpers on my board to begin with. So I'm going to call this first jumper J1. And we need to create an external interrupt input. And we do that by passing in the GPIO that we want to detect interrupts for. We pass in the external interrupt that we're going to use to detect interrupts on that pin. And in the STM32 architecture, you need to use interrupt 0 to detect interrupts on a pin 0, whether it's port A, B, C, D, and so on. External interrupt 1 to detect interrupts on pin 1, and so on. We also need a pull up, pull down, or pull none specified as part of this input. I want to have a pull down set so that they are 0 if not jumpered, because the jumper is going to connect them to 3.3 volts, so that's going to pull them up. So I create the pull down, And now we have our external interrupt object created. And you'll notice that's a generic object, xt_input. So I can create multiple of these and pass them in as the same type into a particular task. So I'm going to spawn multiple tasks, one for each interrupt and an interrupt for each jumper that I want to detect. We'll create that task now, and I'm going to call it jumper, and it's going to take a pin, which is actually going to be of type xt_input, and it's going to need a static lifetime specifier as well. And I'm also going to pass in a name as a static string here, so that when the jumper gets closed and open, I can actually output a nice human readable string associated with that. And this is never going to return. You don't have to add the exclamation mark, the return type, for this sort of task, but if you do so, the compiler will actually check that your function never returns, that you have an infinite loop in there. Whereas if you don't include that, the compiler doesn't know that's your intention, and you could write some code, and your compiler would let you write some code that did actually end up returning. And that's probably not what you want for an embedded application. So the basic external interrupt code is very, very straightforward. We just need a loop, and we need to wait for any edge on that. It's an asynchronous function, so it will yield to the scheduler and only get returned if an edge event happens on this particular interrupt and pin. And then we can log what the state of this pin is. So we can say name changed, and let's output the state it went to. So we're going to need to actually retrieve the state. So let current state equals pin.is high. So this will be a Boolean, true for high, false for low. So if current state, then we want to output high, else we want to output low. And the compiler doesn't like something about what I've written. So this is one of the slight quirks about using deformat. Using the logging crates, logging macros like info, you can actually embed you can inline your arguments within the curly braces. You can't do that with deformat, so you need to put it outside like that. And now the compiler's happy. One more thing we need to do, we actually need to spawn the task associated with this interrupt. So we go spawner, must spawn jumper, and pass in the external interrupt that we created. And if you spell must spawn properly, I reckon it will compile. It doesn't compile because I've not passed a name in. So let's call it J1. Right, the program compiles, and we get one warning, and that's J1 is unused. So I don't know why the compiler is saying that, because it is being used, because we're now using it in our must spawn. So at this point I'm going to restart the Rust server. A quick restart of the Rust server again, and it's now happy with my J1 variable is actually being used. So let's go ahead and flash this version of the application. It's now programmed. We get our new log out, so we can see we are actually running this version of the application. And if I close the jumper, we get J1 changed to high and J1 changed to low. Now we're getting that multiple times, and the reason for that is that the pin is bouncing. So let's add some code to deal with that bouncing. So the easiest thing to do is to add a last state variable, and we'll set that up initially to whether the pin is currently high. And after we retrieve the state of the pin after we get called with an interrupt, we'll see if the state has actually changed. So if current state is not equal to last state, we'll put our log within that if test at this point, and we will also set last state to current state. So now we should only get a single log every time our jumper gets closed, jumper gets opened. Let's program this version of the application, see if that's better. And I'm going to close the jumper. Wrong jumper. There we go, I'm closing and opening it, and we're getting a single log every time it changes state, which is excellent. That's what we want. Final step, I actually have 6 different jumpers on this bit of hardware, so I'm going to create 6 different tasks with 6 different interrupts for each of those. And I'm just going to do some copy and pasting. So I have J1, J2, J4, J8. I have X1 and X2. And they are PB0, PB1, PB2, PB7, PC14 and PC15. They need to be connected to the appropriate interrupts. And then we actually need to spawn the 6 different tasks. So J8, X1, X2, J2, J4, J8, X1, X2. Now, there's one more thing that I need to do, otherwise we're going to hit a panic. And that's tell Embassy that this task might be created up to 6 times. And we do that with the pool size macro variable. So Embassy is creating the objects and allocating memory at compile time for each of these different tasks. It's not doing it dynamically because I don't have a heap in this particular application. So we have to tell Embassy up front how many instances of a particular task type there might be, and then Embassy has the appropriate size allocated for all of its internal management of the tasks and for any stack variables that those tasks might be using. They're not strictly stack variables, there's no stack here for tasks. It's an internal Embassy concept, but I like to think of it as stack. So not getting any compile errors, so this should be good to program. And do the other jumpers work? So let's try J2. J2 works, J4, J8, X1, if I can find it. Excuse me while I swap my glasses. X1, found it, and X2. Excellent, so all of our different jumper pins worked. That does everything that I need this application to do to test the jumpers and the LED of my hardware. Just to recap, how did we do it? Well, we built an asynchronous Embassy application for the STM32 in Rust. We created an asynchronous main function. We retrieved the STM32's hardware peripherals. We created an output pin to flash our LED, and we spawned a task defined down here. Very simple, sits in an infinite loop and flashes the LED on and off with a 500 milliseconds timer in between. Then we created 6 external interrupt inputs, one for each of the jumper GPIOs that we wanted to detect being closed and pulled up, and connected those pins to particular hardware interrupts on the STM32. And then we spawned 6 different instances of the same task, passing them in those different external interrupt inputs, and had a very simple infinite loop in each of those tasks that sat there and waited for an interrupt on our pins either going high or low, and then logged if the state had changed from the last state they'd been called with. What did that take? 60 lines of Rust, and frankly 60 lines of really straightforward Rust to use hardware interrupts and GPIOs on the STM32. It's this ease that's actually now led me to using Rust as my go-to for simple applications, and actually some quite complicated applications on embedded environments. The only time I use anything other than Rust is when I need something that's really performance critical, like the implementation of the software-defined retro ROM itself, the hardware that we've been testing here, and I need to be absolutely certain of the performance down to the number of cycles
that the CPU is using to execute my code.
Anyway, I hope you found this video interesting and useful. If you did, please do consider sticking around. Till next time, rock on.